In this video, we'll talk about volumes of revolution. So I want to begin this with an example, which says, let S be the region bounded by y equals square root of x plus 2, the x-axis, x equals 1, and x equals 9. Find the volume obtained by rotating S about, part A says, the x-axis. All right, so I want to begin by drawing a picture. So I'm going to draw some axes. So my y-axis and my x-axis. So the graph of square root of x plus 2 will look like the square root of x graph, but the plus 2 will shift it up 2 units. Okay, so this intercept, this y-intercept, is going to be at 2 now, instead of at the origin. And it'll curve like this, just like the square root of x graph does. And we need also to draw x equals 1 and x equals 9. These are vertical lines. So that curve, those vertical lines, and the x-axis, they bound this region, and that is this region S that the problem is talking about. Well, then it says, rotate this region about the x-axis. So we are going to be rotating this thing about the x-axis. So here's how I'm going to draw sort of a shape, draw that and make it look 3D. So what I'm going to do is take this whole region, reflect it across the x-axis. So when I do that, I like to draw dashed lines for the reflection. So I'll draw a dashed line here for this reflection, dashed line here. I know this one's going to go a little bit further down, just like this one goes further up in this direction. And then I draw the reflected version of my square root x curve. Sorry, square root of x plus 2, just flipped. All right, and now I'm going to draw some of these cross sections. So I'm going to draw the one at this end. If I rotate this point about the x-axis, I'm going to draw what it will look like. It'll sort of curve like this, reach that bottom point, and then it'll curve behind, and I won't be able to see that, but it'll make the circular shape when I rotate that about the x-axis. Similarly, this point will curve down, it'll reach that bottom point, and then it'll curve back. It'll curve back and make a circle. So now what I'm going to do is, at some arbitrary x coordinate here, I'm going to draw a cross section. Okay, so at that top point here, that'll come down, and I'll reach the bottom, and then I'll have the back. So it'll make this circular cross section. But to talk about volume, I need to give this cross section a little bit of thickness. Okay, so I'm going to give it a little bit of thickness. So that thickness will extend in the x direction here. Okay, and I'm going to call that thickness dx. The dx is kind of like delta x, but it just indicates that it is really, really small. Okay, and now let me label the radius of this cross section, the circular shape, as little r. All right, so let's write down our formula for volume. So our formula for volume, because my thickness is in the x direction here, I'm going to have a dx integral. And we're going to be integrating the area of this cross section. I'm going to call that a of x. We're going to write it as a function of x because it's a dx integral. And then my limits of integration go from, well, what is the smallest x can be here, which is 1. And the biggest x could be is 9. So this next part is important, and it's purely for visualization. I want you to pause the video for 30 seconds and see if you can just convince yourself that you know what the graph of this looks like, what this 3D shape looks like when you took that curve, this whole region S, and it got rotated about the x-axis, that you have an idea of what that shape looks like. Pause it in 4, 3, 2, 1. Pause it for 30 seconds just to think about that. That's maybe the hardest part of this, just being able to visualize what this thing looks like. And we'll do more practice problems, but after we do them, if you still have other questions about it, definitely come and ask in office hours and in tutoring. That's super important. Alrighty, so let's evaluate this. We got the integral from 1 to 9. The area of this cross section is pi little r squared, and then I have dx. Okay, so I need a way to relate little r to the variable x. Okay, so this point here that's on my curve, if I call that x comma y, my radius, little r, is just that y coordinate, how high up this is. But I don't just want to plug in y, because then my variables are still mismatched. But I know what y is in terms of x. Y is square root of x plus 2. So that is what I'm going to get to plug in. All right, so this is going to give me the integral from 1 to 9. Let's pull out the pi because it's a constant. and then we'll get r squared, which is square root of x plus 2 being squared, dx. All right, so if I simplify, we get pi times the integral from 1 to 9. And if I square this, if I expand it, I'll get x plus 4 root x, which is 4x to the 1/2, plus 4 dx. Now I can do the antiderivative. So I get pi times, I'll get x squared over 2 for the first term. Then I'll get 4 times the antiderivative of x to the 1/2. So I'll get x to the 3/2. And when I divide by 3/2, that's the same as multiplying by 2/3. And then for the plus 4, that antiderivative is 4x. All right, and of course I got to plug in the 1 and the 9. So if we plug 9 into this, we'll get the pi, stays outside. Plugging in 9, we'll get 81 over 2 plus 8/3. And then if I do 9 to the 3/2, that ends up being 27. Plus 4 times 9 is 36. So we get that minus what I get when I plug 1 into this thing. So I'll put a parentheses, and I get 1/2 plus 8/3 plus 4. And then close that bracket. Notice I could just keep pi outside of everything. It was factored out of everything here. So at the next step, I also just kept that pi factored out. All right, let's continue to simplify. This will give me pi times, so 81 over 2 minus 1/2. That is 80 over 2. Then 8/3 times 27 is going to become plus 72. Because I could cancel these a little bit and be left with a 1 down there and a 9 up here. Then I get a plus 36. We're going to get minus 8/3. And we'll get minus 4. All right, so this becomes pi times, and if I combine all the integers, and 80 over 2 becomes 40, I will get 144. And then we have that minus 8/3. And getting a common denominator, this will become 424 pi over 3. And that is our volume. All right, let's do another example. Now I want to rotate this whole thing about the y-axis. But this time, just set up an integral. No need to actually do the antiderivative. Okay, so let's draw a picture again. All right, so I'm going to draw my axes. This time I'm going to draw more on the other side of the y-axis because I got to rotate it about the y-axis. So my region, remember my square root curve looks something like this. This is at 2. Then I draw 1, then I draw 9. Draw these vertical lines. So we have this region that's bounded by these curves. And now I'm going to draw the mirror image of that across the y-axis because I'm rotating it about the y-axis. By the way, I draw these curvy lines to indicate what is it, what am I rotating my shape about? In this case, it's about the y-axis. In the last problem, I drew that curvy line about the x-axis. Okay, so let me draw a mirror image of this shape first across the y-axis. So I'll draw this line, and then I'll draw the one over here that was at 9, and then I'll draw the square root thing, mirror image. And now what I'm going to do is I'm going to draw some of these cross sections. So my cross sections, if they're up here, they would look something like, if I take a point like this and I rotate it around, it would reach this side and then it would come back around. But if I take a point sort of further out like this, at this further end, and I rotate that around, it would make it all the way to this side. And then I bring it back around like that. So my cross sections sort of have this shape. It's like a circle with a circle missing. And of course, there's going to be a little bit of thickness. But the thickness right now is going to be vertical. So our cross sections will have this thickness like this. And this one I'm going to call dy because it's in the y direction. So our cross sections here are what are called washers. So washers are these tools that we use with screws when we screw screws into things. Okay, so from the top view, there's sort of like a small circle, and then there's this larger circle. So the region we have is just the stuff that is sort of in between the two circles. Alrighty. Okay, so if I write down my formula for volume, I'll get an integral. This one's going to be a dy integral. I'll need my area formula. This time it's going to be in terms of y, because it's a dy integral. I know it's a dy integral because the thickness of my slice is in the y direction. All right, and then it'll go from some number, I'll call it c, to some number, I'll call it d. Okay, and so the limits of integration have to do with, well, what's the smallest y's in this region? And what's the biggest it is? So the smallest I can see, well, that's down here, that's 0. And the biggest has to do with what the coordinate is at this high point. So the x coordinate here was 9. And if we plug that into our square root equation, it was square root of x plus 2, if I plug it into there, we'll get that the y value is 5. Okay, similarly, for this point, maybe we'll need it. Let's see, the x coordinate is 1, and if you plug that in, the y coordinate would be 3. Okay, so my integral, that upper limit will be 5. All right, and now my area formula is the area of this washer. So to get the area of the washer, I'm gonna call this small radius little r, and the big radius I'm gonna call big R. So the area of the washer is gonna be pi the big radius squared, and then minus pi the little radius squared, and then we'll get dy. If I factor out the pi from both of these terms, I can pull that all the way to the front and get pi times the integral from 0 to 5 of big R squared minus little r squared. Okay, so if we look at the picture, let's label big R and little r. So my picture, big R would go from here all the way to this edge, and I know what that is. I know big R is just 9 looking at my picture. Oh, what about little r? So little r, well, in my picture, little r goes from here to here. Let me label that. But if my washer, if my slice goes below this point, those washers will look different. Let's see, so if I draw them a little bit lower, this would be sort of the, how far the inner radius goes. I'd have something like this. And the outer one would go somewhere out here, and my washer would look something like that. And again, it would have a little bit of thickness in the y direction. A little bit of thickness. Okay, so we have this. So for this washer, this would be my little r. And the big R would still be that distance. It would still be the same. So the issue we're realizing is that little r changes at some point. On this blue, this bottom cross section, that little r is just 1. So it changes from r equals 1 to what it is on this upper cross section. On the other upper cross section, it depends on the coordinates of this point. If I call this point x comma y, that distance, little r, is just the x coordinate. Okay, so my r changes from r equals 1 for the bottom portion to this upper cross section. My r value becomes my x coordinate on that curve. Okay, so this means we are going to split up our integral into 2. We will split into 2 integrals. Okay, but it's not too bad. We can handle that. We'll get pi in front of the first integral. So we would get pi times like the first integral, some stuff, plus the second integral, some stuff. So I can distribute the pi to both of these terms. So when we do that, we'll get pi times the first integral. So let's see. If I think about these slices, my little r would stay just going to 1, this vertical line, until I got to this point. And at that point, the y coordinate is 3. So from 0 down here to 3 up here, we get 1 value of little r. So on that interval, my big R is 9. We get 9 squared. And then minus my little r is 1. We'll get 1 squared dy. Okay, so this is big R squared, and this is little r squared. Okay, and then we'll get plus. Remember, the pi distributes to the second integral as well. And for the second integral, that one starts at here, my y value is 3, and it continues up to this point where my y value is 5. So I'll get the integral from 3 to 5. My big R squared, I'll still have 9 squared. The big R doesn't change for those upper cross sections. And then minus, I need little r squared. I'm giving myself some extra room here. So my value of little r here is x, but I don't want to plug in x because this is a dy integral. So I need to figure out how to relate this x to that y coordinate. So I'm going to use the equation. Actually, let me just write down what the equation was. So let me erase this to give myself some room. Okay, so my equation was y equals square root of x plus 2, and I'm going to isolate the x here. So I'll get y minus 2 equals root x. And if I square both sides, we'll get y minus 2 squared equals x. Okay, so that is what this x value equals. It's y minus 2 squared. And now I can plug that in for the little r. So we will get, let's see, we'll get y minus 2 squared, that's little r, being squared. So there are two squareds here. This is little r being squared. So remember, this problem just said to set up the integral. At this point, we've done that. So we could evaluate this antiderivative if we needed to find the actual volume. And if we work out what this is, it ends up being 1768 pi over 5. All right, let's do one more part to this example. Now I want to rotate the shape about the line y equals 10. Again, just set up the integral. So I'm first going to draw a picture. So I'm going to draw my y-axis, my x-axis. Let's draw the shape. So we get something like this. And this is, I know, 2. Here's 1. Here's 9. Let me draw these vertical lines. And I know these points. Let's see, I know this point was at 9, 5. And I know this point was at 1, 3. So now I'm going to draw the line y equals 10. So y equals 10 is going to be above the y coordinate here, which is 5. I'm not going to draw it to scale. Let's just say it's kind of close. So let's say this is where 10 was, and I'll draw a dashed line for y equals 10. So I'm going to rotate about this line, y equals 10. Okay, and when I do that, I want to give you an opportunity to draw what that would look like, as well as the cross sections. So I just want to give you a couple minutes to try drawing the picture. Okay, so I want you to pause the video for 2 minutes to try that. 4, 3, 2, 1, 2-minute pause to see if you can draw the picture. Alrighty, so hopefully pause it for about 2 minutes. Let's do it together now. So I want to first draw the mirror image of this across what I'm rotating it about. So across this line. So I'll have something like this. It'll extend down. And then this point, when I reflect it, will be sort of further up than this point was. All right, and I draw a horizontal line that's kind of like the bottom of this region. And then I draw a curve to be like the mirror image of this square root curve. And now I'm going to draw one arbitrary cross section. So an arbitrary cross section. Okay, so if I were to take a point like this, and I rotate it, it would get rotated. It would reach the top point, and then it would come back down. And then if I take a point directly underneath that, here, and I rotate that all around, it'll come all the way up here, and then rotate back down. All right, so now I'm going to give this cross section a little bit of thickness. Okay, so this is going to have a thickness in the x direction, a horizontal thickness. Horizontal thickness. And my cross sections are washers again. Okay, so here's the center of both of the circles. So I'm going to draw the small radius and the big radius down to the original region. I'm not going to draw it to the reflected area, just because I know the curves in the original region. But in the reflected region, I may not know these equations. At least for the square root part, I may not know that. Okay, so this is going to be my little radius. And the big radius goes from the center all the way down here. So if we set up our equation for volume now, we get V equals, I want to again give you 2 more minutes and see if you can set up the integral from here. Pause it in 4, 3, 2, 1, 2-minute pause. See if you can set up the integral from here. All right, so hopefully you tried that. Let's talk about it together. So I'll get an integral. It's a dx integral because the thickness here, let me indicate it, is a dx. It's in the x direction. All right, and then I have to have my area function, which is in terms of x, because it's a dx integral. And my x values sort of start at 1, and they go until 9 here. I don't have that issue like we did in part B, where the small radius will sort of change. It's always kind of going to this square root function. or where the big radius will change, because it's always going down to the x-axis here. So I'll just need one integral. All right, so for the area of my cross-section, it's going to be the area of a washer, okay, which will be pi big R squared minus pi little r squared. Let's factor the pi out. I'll get big R squared minus little r squared dx, integral from 1 to 9. So we'll get pi, integral from 1 to 9, big R. I know this vertical distance goes from the x-axis up to where y is 10. So that distance is 10. So I'll get 10 squared for big R squared. And then I need minus little r squared. I'm going to give myself some room here. So for little r, it depends on a couple of things. It depends partly on, well, how high up is this point, the center of the circle? So I'm going to call that point x for the x-coordinate, and the y-coordinate I know is 10. So that is x comma 10. And this point directly below that on the curve, I also need to know that. That has the same x-coordinate as that point above it, x. But the y-coordinate, I don't know. I'll just call it y. But I do know what that y-coordinate is in terms of x. So I can call this x comma, and I know y equals square root of x plus 2. Okay, so using that, my r value is going to be sort of the difference in these y values. It's going to be 10 minus, and the smaller y value was root x plus 2. Okay, so that is what I'm going to plug into this parentheses. 10 minus parentheses root x plus 2, close that parentheses, that whole thing being squared. The problem just said set up the integral, and now we've done that. If we needed to evaluate what this was, I'll put a dot, dot, dot. It turns out it is 1576 pi over 3.